Okay, if there are no questions, then let me start with a lecture on derivatives. So what I want to do today is sections 3.2, 3.3, and 3.4. So these are the main sections on taking derivatives. And it's also the material you will have to use in this week's WebAssign homeworks. So it's the basic rules of differentiations. So let's first recall what we know so far. So the first thing is everyone should know what the derivative of a function is. So everyone in the class is expected to be able to explain to a 9th grader who knows what the slope of a line is, how one computes the slope of a curve. It's the story with zooming into a graph at a point X, looking at the graph closer, and if the graph looks locally like a straight line, this is a way how to compute the derivative of that straight line, also called the tangent line. Then we know for a certain class of functions, power functions, x to the alpha, that one can compute the derivative as alpha times x to the alpha minus 1. And there will be an extra homework assignment where you can make extra points, where you prove these statements in detail. So basically we have proven it by example. We did x to the 3, x squared, square root of x, x to the minus 1. And we saw that this rule always holds. But there is a formal proof that with what one can show that it holds for all alpha, and this will be one of the homework assignments. And the third thing, what we know, if you take f of x equal to e to the x, where e is the number 2.71 to the x, and this can be computed as the limit if n goes to infinity of 1 plus x over n to the n. And if you graph this function, it looks like all other exponential functions. With the only difference, or like all exponential functions, that it grows pretty quickly. So if x is 1, you are at 2.71. If x is equal to at 2.71 squared. But then already if x is equal to 10, you are way above the building. You are way above the highest high-riser in New York City. And if x is equal to 20, you are on your way to the moon. And if x is equal to 100, you are out of the universe. So it's a very rapidly growing function. So these are all the functions we know how to take the derivatives of. And today we expand the range by a factor of 1,000,000. So we have now certain rules which one can compute the derivatives of all functions. In the first rule, we have this is the product rule. So if you have f of x times g of x, and you take the derivative of a product. So if you have a product of two functions and you take the derivative, then it's the same as the derivative of the first function times the second function plus the first function times the derivative of the second function. So this is the first fact you have to know. In the second fact, you have to know why this is true. Okay, now you don't have to write this here. Again, I will post the PDF file here. It's a lot to write if you write this now. Try to understand what's happening there. So how does one compute a derivative? Yeah, so you go back to the definition. The derivative is a limit of the differential quotients. So this is the same as the limit, if h goes to 0, of f of x plus h times g of x plus h minus f of x times g of x in the whole thing divided by h. So it's like other derivative. You evaluate something at the value x plus h. You subtract it at the value of x. That gives you the rise. In the run is then x plus h minus x, which is h. It's rise over run. And you do this very close to the point x. If you plug in for h equal to 0, the top will be 0. The bottom is 0, so you get 0 over 0. So this does not work. So you have to do algebra. In the algebra you do now is here. So first of all, I make a longer fraction sign. Then I have the f of x plus h in the g of x. And I have the minus f of x, g of x, and I divide it by h. So it's the same, I didn't change anything. And I left the space in the middle because I can add or subtract 0. It doesn't change anything. So now I subtract here. So I subtracted the term and I added the same term. So I didn't change anything. It's still the same expression. But now I can factor out so if I look at the first two pieces, this is the same as f of x plus h minus there I made a mistake, sorry. So I had f of x plus h, g of x plus h. So I forgot here my h. So I have here f of x plus h minus f of x over h times g of x plus h plus, and now the second piece here is f of x times g of x plus h minus g of x over h. Again, if you look at the red piece, the g of x plus h is in both terms. I can factor this out. And if you look at the green piece, the f of x is in both terms, so I can factor this out. Now if h goes to 0, then the first term is f prime of x. And if h goes to 0, the second term becomes g of x. And in this thing here, the green term, if h goes to 0, you have f of x. In the second term is g prime of x. Now, no one has to remember this. No one has to know it. What you should remember, the product rule holds. Because if you take a product and plug it into the definition and you do the algebra, then this is what you get out. So the product rule just encapsulates what you would get if you would do the algebra. And a rule is a rule. A rule means we think about it once, we make it sure once that a rule is true, and now we can avoid using the limit, and now from now on we use the rule. So whenever you take a derivative of a product, we no longer have to use the definition. The definition applied to this product becomes the product rule. So let me do the next rule. If you have a quotient, and you take the derivative of a quotient, then you get, again, a quotient, where the easy part is the denominator is nothing else than g of x squared. So you square the bottom. And the top is the same as the product rule, except you have a minus. It's the derivative of the top times the bottom minus the top times the derivative of the bottom. Now this looks strange, this looks very strange, but the explanation is now because if you take the definition of the derivative, and you look at the differential quotient and see what happens if h goes to 0. Now you have to do a lot of algebra, a common denominator, including terms, taking terms away. You do some algebra, you fight your way through it, and after 5 minutes you get out, it is the same as f prime of x, g of x, minus f of x, g prime of x, over g of x squared. Okay, that is the quotient rule. Now let's go to the last rule for today, that is the so-called chain rule. So again, if we go back, this is section 3.2. The quotient rule is section 3.2. And before we do example, let's go to section 3.4 and let's do the chain rule, maybe the most important rule of all. So the chain rule is if you have a function f applied to g of x. So you start with an x, then you first apply the function g, and then you apply the function f. So you have a chain of operations. First g, and then f. And you take the derivative of such a chain. Then this will be the same as the derivative of f. So it's the derivative of the outside function applied to the inside function times g prime of x. And again, the statement is this is true because the limit, if h goes to 0, of f at g of x plus h minus f at g of x divided by h, when you do the algebra, and out you get the derivative of the outside times the derivative of the inside. So now I want to do for 10-15 minutes examples for the product rule, the quotient rule, and the chain rule. And you will find another 80 examples in the homeworks. Not 80, but at least 30 examples you have to do in the homework. And then at the last 10 minutes of class, we cover the derivative of the sine and the cosine. Now, examples. So there are now two ways to compute the derivative of this function. One way would be that you multiply everything out. And if you multiply everything out, the highest term would be x squared times x to the 3, x to the 5. And the lowest term would be minus x. So after you multiply everything out, you have a polynomial, and then you could use the power rule. Correct? But this is a lot of work, multiplying the things out. An alternative way would be to use the product rule. Now the product rule says, I'm sorry, let me call this h of x. So h of x is f of x times g of x. So the function h is a product. And if I take the product, the derivative of h, it is the same as I take f times g prime. And now you have to memorize that the derivative of a product is the same as the derivative of the first times the second plus the first times the derivative of the second. So in our case, h prime of x is the derivative of the first function of x squared plus 3x minus 1, which is 2x plus 3. X squared, the derivative is 2x. The derivative of 3x, the slope of 3x is 3. And the derivative of a constant is 0, because the slope of a constant function is 0. So it's the derivative of the first times the second plus the first function times the derivative of the second Wait, there is something wrong. Well, so here is the derivative, where you didn't have to multiply everything, so you get a formal piece of the derivative without multiplying it out first. Let me do a second example.
Wait, question.
Yes.
At that point, since you have the derivatives of f and g, you wouldn't have to expand the equation anymore. That would be a derivative right there.
So the question is an important one, so let me write it down. So if I reword the question, the question would be, if you have the derivative, do you have to simplify it? In this case, would you have to multiply it out? And the unfortunate answer is yes. Taking derivative would be easy if you would just have to compute the derivatives without having to simplify it. Simplifying means you have to factor it. The main challenge in taking derivatives is not taking derivatives. The main challenge will be that you have to simplify these terms, and this is where all the problems come in. So in the beginning, just not to overload you all, I just want to take the derivative. But the real problem, also the real problems in the homework will be that you have to simplify it, and we talk about this later. So the answer is yes. And that is the real problem in taking derivatives. It's not the calculus piece, it will be the algebra. So maybe an easier example and make it clear what happens if you take h of x equal to x squared times e to the x. Okay, first question is, for which values of x is this function defined? What is the domain of this function? X squared times e to the x. Certainly you can plug in all positive numbers. Can you plug in a negative number? What is 10 squared times e to the minus 10? That is the same as 10 squared divided by e to the 10. So yes, it's defined for all x. The domain is all x. What is the limit of h of x if x goes to infinity? If x is a big number, like 10, like 100, you have 100 squared times e to the 100, yeah? So this is huge, that will be plus infinity. In the limit, if x goes to minus infinity of h of x, then the x squared is again big, but now you have e to a power of a negative number. So let's take x equal to minus 100. Minus 100 times minus 100 is 10,000. So minus 100 squared is 10,000 times e to the minus 100. So this is 10,000 divided by e to the 100. And e to the 100 are about 25 light years of units. No, yeah, 25 light years of units. So e to the 100 is a huge number. So 10,000 divided by this will be 0, so this goes to 0. And you see, this is stuff from chapter 2. In each and every homework problem in calculus, you have to take limits. Because these two numbers tell you now where the graph starts and where the graph ends. So we have that h of x is always positive. X squared times e to the x is always a positive function. It will start at 0. If x goes to minus infinity, you are at 0. And if x goes to plus infinity, you are up here. You go to plus infinity. And you know the value at 0, x squared times e to the x is equal to 0 if and only if x is equal to 0. So you look at the endpoints of the domain. The domain of the function goes from minus infinity to plus infinity. So you have to know what happens at the left end of the domain. There the function is at 0. At the right end of the domain at infinity, the function is at infinity. And the zeros are, the only 0 is at 0. The product is 0 if one of the terms is 0. E to the x is never equal to 0. X squared is 0 if and only if x is 0. Okay, now everyone draw a graph that is always positive. Starts at 0. If you go to minus infinity, it's 0 here, and then goes to infinity here. So you take a pencil and a paper and draw a graph without breaking your wrist. a continuous graph that is always positive, starts close to 0 at minus infinity, is 0 at 0, and then goes up to plus infinity. Now, this is still speculation. I mean, I could have a graph that looks like so I have to start here. It's always positive, and I have to go up here. So there are many possible graphs. So I could also have something like this. So this one here would be the easiest, yeah, possible graph that has this behavior. If I only know that I start at 0 it's equal to 0, and then I go up to infinity. So there could be lots of wiggles in between. But just looking at the function itself, a possible graph looks like this. And if you want to do it more fancy, it would be like this one here. Now, to make sure that it is the first one and that the second one, now we have to compute the derivative to see where are the maximas and the minimas of this function. The first function has a local maxima at a negative x value and a local minima at 0. This second possibility here has lots of local maxima and minima. So if we know the derivative, we can rule out the second option and decide for the first option. Now, if you take the derivative of this function, then you have a product where this is the first function and this is the second function. The derivative is the derivative of the first function times the second function plus the first function times the derivative of e to the x. But the derivative of the exponential function is the exponential function. So you get 2x times e to the x plus x squared times e to the x. And now, in order to see where the first derivative is 0, where the first derivative is positive or negative, you must simplify. Now, in this case, the simplification, which always means you try to factor, is easy because if you factor, you can factor out an x term, you can factor out e to the x, and what you are left with is 2 plus x. Again, 2x e to the x, x squared e to the x. In both terms, you have an e to the x. You can factor this out. In both terms, you have an x term. You can factor this out. So that's what your result is. Now you draw your number line. And you look at the first derivative and see where is the first derivative equal to 0. Yeah, x is equal to 0 when x is 0. So we have at 0 is a 0. And if x is equal to -2, we have a 0. If I plug in a number to the left of -2, let's say -10, then I have -10 times e to the -10 times -8. So it's negative times positive times negative. So it will be positive. If I plug in a number between -2 and 0, let's say -1, then I get negative times positive times positive. So the whole thing will be negative. And if I plug in a number to the right of 0 into the first derivative, let's say 2 or 3, then I have positive, 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 everything is positive. So if the derivatives are positive, then the function itself must be increasing. If the slopes are positive, that means the function is increasing. If the slopes are negative, the function is decreasing. And if the slopes are positive, the function is again increasing. Now, what does it mean? If to the left of -2 you go up, and to the right of -2 you go down, then you must have a maximum at -2. And at 0, to the left of 0 you go down, to the right of 0 you go up. So you must have at 0 a minimum. So let's going back to our graph. At 0 we have a minimum. At -2 we have a maximum. The slope at -2 is 0 because you have a horizontal tangent line. The slope at 0 is 0 because you have a horizontal tangent line. And if you want to know the value at -2, now you take the -2 and plug it into your function. Then the value here is 4 times e to the -2. -2 squared times e to the -2. So this is about 1/2 or something like this. So the maximum is at 1/2. The maximum occurs at -2, and that will be the shape of the graph. And now, since you know the graph, now you can turn a graphing calculator and confirm that the graph really looks like this. So this is not a graph, this is a sketch of the graph. And you see the important thing of the graph should be happening around -2, and there you should see a local maxima. Now for this function, a graphing calculator would have been completely fine. Every graphing calculator can do this. If I give you the function x squared times e to the e to the 100x, or x squared times e to the x to the 100 or something like this, that this is outside of the capabilities of any graphing calculator, but you can still sketch the graph by using these methods. So the main question is the translation from an algebra expression into a graph, into a geometric expression, is easy for function like x squared, like parabolas, x to the 3. For more complicated functions, that's a difficult process to visualize algebraic expressions. In some cases, calculators can do it. In most cases, calculators will give you a very, very rough idea, and in many cases, the wrong idea what the graph will look like. Okay, now I will not go into further details. Let me go now to examples. We do examples the whole week. We do nothing but examples. It will always the same thing. You start doing examples with 3.2 as soon as you can. Now, one thing is in 3.3, and I will prove this tomorrow. So what you have missing is if f of x is equal to the sine of x, yeah, where you have here pi over 2, 3 pi over 2, and 2 pi. So it's the sine function where x is measured in radians. So we have to recall tomorrow what is the difference between radians and angles. Then f prime of x is equal to the cosine of x. And why is this true? In this case, we don't do algebra. In this case, we have to do now some trigonometry. And if you think about, there are formulas that sine of x plus h is the same as sine of x times cosine of h plus cosine of x times sine of h. So these are the trig identities. So now in this case, we don't do algebra. Yeah? And then if you do some trigonometry, then you will get out after some while that is nothing else than the cosine of x. What is the slope of the sine function at 0? Yeah, it's positive. If you look at it closer, it looks like the slope is equal to 1. And that's the case because f prime of 0 is the cosine of 0, which is equal to 1. So you can compute the slopes of the sine function with the cosine function. And if you do the cosine function, then you get that the rate of change of the cosine function is minus the sine function. Again, these are properties we'll prove tomorrow. And then you are done with chapter 3. So these are the main ingredients of chapter 3. It's the rules of differentiation, plus you have to know the derivative of sine, the cosine. Then the tangent is sine divided by the cosine. So there we can use now the quotient rule, then we get the derivative of the tangent. The cotangent is cosine divided by sine. So you use the quotient rule, you get the derivative of the cotangent. So if you have the derivatives of sines and cosines, you can compute all other derivatives. And then we have a few more applications, but the main rules is what we cover today. And the main thing of chapter 3 is that you have to practice these rules. Okay, so this is all what I want to do today. It's 8:17. Tomorrow then examples, 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 how to use the rules and how to simplify derivatives. Thank you all.